overview of what we see as the challenges in big data analytics, some of the lessons we've learned here in the PROTECT Center, and then I'll pass it on to my colleagues Justin and Jennifer to talk to you about some of the tools and techniques that they use in their work as they explore data. Okay.
Dave, you may need to click on the slide with the there you go.
Very good, thank you. So here's an overview of what this webinar will be about. So basically, we're going to be talking about data. Data is the key. We're creating more and more data. So some of the data processing tools and techniques that we use, where we can go off and pursue data-driven discovery. We're going to talk about biostatistics, some big data analytics, data mining, and machine learning. So basically, the key topics, we're going to talk about how we go about cleaning, wrangling, managing, processing large amounts of complex data, and then more importantly, how we then, since we have appropriate data, we can start to extract value and knowledge from this data. So just to set the stage, I think there's this growing trend in every field, but particularly health data, where we're seeing more and more investments in the creation of knowledge through data. These are just some statistics. $4.2 billion was spent in 2017 on expenditures on big data in healthcare, and this is going to grow to over $68 billion by the end of 2025. If you look here on the right, the amount of different types of data, the sources, the capabilities, the stakeholders, I think we're just seeing this explode. And so it's critical that all of us take data management and data analytics and machine learning really seriously, because this is not something that's going to be the future. It's today and it's here and now. So we need to learn about it. When we talk about data, we usually talk about some of the challenges with data, and this really has impacted how our day-to-day within the PROTECT Center, but also in any data-related or environmental health-related project. We deal with a wide variety of data. We're dealing with, in environmental health, we're dealing with the environment, and we're dealing with personal health. And so that includes a variety of data that comes in different formats, types, and structures. It may be images, it may be numerical or textual data. It can be social media data. Some of it is static, some of it is streaming data, continuous things that are tied to weather, environment, or continuous. Some is numerical, some is categorical, depending on how that data is being acquired. And again, so our challenge is, how do we, how can we extract knowledge? Somehow we have to be able to link this data together and bring in a common model so we can analyze the data and do it appropriately. So, a second aspect of data today is the volume of data, the scale of data. This is becoming more and more of a challenge. Why? Because we're just seeing this explosion in ways we can acquire data. Every one of our instruments now is, I have my Fitbit on, it's generating data continuously. Our instruments and sensors, their resolution, their accuracy, it's just increasing. Social media, obviously, every day we have billions and billions of bytes being generated, and then the ability to be mobile and portable. So we don't have to have fixed acquisition anymore. We have the internet, we have wireless, we can basically get information and data anywhere and any time. So, we're up into the zettabytes of data now in 2018, and this is just going to continue to increase. Finally, we talk about the velocity of data. This is the rate of data that's coming in. So a lot of the applications we deal with are real-time streaming data. The problem is it doesn't stop, and we'd like to make decisions on that data now. We need ways to get our arms around this so that we can, to make some decisions, not 2 weeks from now or a month from now, we'd really like them to be in the loop, the computation. So what we need there is high-performance computing and parallel computing. It's a project that Jennifer and I have ongoing, funded by NSF. But again, with things like your healthcare monitoring, that is a continuous stream of information. How can we react to that information in a timely fashion? So let me set the stage by talking just for a second about the PROTECT Center. So basically our goal is looking at the linkages between a large potential contributing factors that influence premature birth. And we're looking at northern Puerto Rico as our site. As part of that, we work with all of the cores and the projects, but we're the data management and modeling core, and we're in charge of collecting, cleaning, managing, securing, and analyzing massive amounts of data from a wide range of exposure sources. And again, we're not just looking at the exposure, we're looking at biological samples, we're looking at weather, we're looking at water, we're looking at all types of data here. Some of the things so this just sort of gives you the scope of the kinds of data that we deal with: human subject, environmental, targeted biological, and non-targeted biological. One of the key things that any environmental health project should adopt is developing a data dictionary, a vocabulary across your projects, your centers, for talking about data. And here's our view of our data over here on the right, this visual, which really nicely captures how we actually index all of our data. Every piece of data has a name, an index, and can be cross-referenced either by human subject ID, which is generally the participant mother or the child involved, or by a location. And so now we have sort of a global map of our data, and we can do cross-indexing, we can query it, we can do all types of analysis. So now we have data, but is this good data? Is this useful data? Well, one of the challenges that we have to do with all of our data is looking at data quality and then data cleaning. So data quality, we're actually sampling the data to see whether whether it follows some trends, whether it's within bounds. We've developed a management framework that's built on EarthSoft's Equus software that basically allows us to work with all of the different projects and sites that we work with. We're a distributed center at PROTECT. And so we bring in things such as questionnaires and medical records, as well as things such as medical samples from, or biological samples from blood or water or urine. We basically have to clean this. So we basically have to bring this in and with a set of rules, judge whether the data is correct. Why is it not correct? Well, a lot of it's transcribed from forms to spreadsheets. Sometimes the data is missing. Why? Because it could be a participant dropped out of a study. It could be for a variety of reasons, or maybe that field just wasn't applicable to that particular person or thing. Out of that, we're able to then build clean data, a whole repository. We use SQL Server as our database engine, and then on the back end, we're able to provide to our users through a set of analytical analyses, visualizations, and mappings, sets of tools that they can actually go through and discover trends and patterns within the data. So our workflow looks something like this. We basically have a front-end data management system where we bring in raw data. We basically do our data integrity checking. We also have this real-time interface, web-based interface that we can do visualization and data reporting. And then on our back end, we have analytical tools where we can, again, those are types of tools I've just been talking about, where we're doing a lot of the analysis, and then we can tie to machine learning tools. In terms of the workflow, so again, our data dictionary drives everything. Without this data dictionary, we'd be lost as a center. We would not be able to take the different, we could solve problems specific to a project or a core, but to have those cores work together and find the interrelationship between water and products and all types of factors that could be contributors to preterm birth, we really need this data dictionary to help tie it all together. That allows us to build an XML schema to actually describe in a data table how each of these fields are related to each other. We use a number of tools. We use Visual Basic for cleaning our data, for doing data conversion, SQL for building queries. We use within Equus Enterprise dashboards for building web-based queries that are automated for the different constituents within our center. So one of our biggest challenges is harmonization. So what's nice about PROTECT is we have basically a single cohort. We also have CRECE, which is the children that basically are born, and we follow them for a number of years and collect data on their development. Tracking all of this is challenging. Harmonization is the process of trying to take two cohorts and actually bring them together so that we can do a cross-cohort study. It's a very challenging thing. We're actually going through this process right now because we're part of the NIH ECHO project. And one of the big benefits that we have is we have this data dictionary that guides us. It gives us a map of our own data, and we can map our data to the ECHO protocols. But we do find that we have a number of incomplete records, and we need methods of handling missing data. We have unbalanced data sets. In terms of the term and preterm participants, we basically have many more term than preterm, thank God. So if we're going to pick a good either statistical or machine learning method, we have to consider about how this may affect overfitting of the model. We also have challenges with numerical and categorical data, so we need to transform the categorical data into something we can actually analyze with machine learning techniques. So in terms of missing data, we basically have built a processing pipeline where we actually filter out text-based data entries. We filter out data that has less than 80% completion, both as we look at a particular sample or in a feature within that data set. So we sift out features and samples, and basically these won't get into our data sets that we're actually going to start using for machine learning. So we've built a whole protocol there. Secondly, we're looking at how to handle individual fields where we're missing data. So again, if we have a high degree of missing data, we remove it completely. If we have just a few that are missing, we basically use a similarity measure that, first of all, for categorical data, we have to use a one-hot encoding format. That's a fairly standard technique that's used to take the categorical data and map it to a numerical value that's not necessarily a range, but in a one-hot encoding. Then we actually build a similarity matrix sample by sample using a simple equation, basically doing a dot product that looks for what the distribution of that data looks like, and then we find when we have a missing value, we use the nearest neighbor value for filling in that value. Once we have that, then we have a completed data set, and we can start to do our data analysis. With that, I'm going to stop and pass this to Justin, who's actually going to talk to you about a lot of the biostatistics and other techniques that we use within the center. So Justin, give us a second to share.
Thanks, Dave. Okay, so thank you. That's a great introduction to talking about the biostatistics portion. As we rely heavily on getting accurate and as complete as possible and as clean as possible data for our analyses. And the focus of my talk will be a little bit to set up Jennifer's talk later on the differences between sort of biostatistics and machine learning. So biostatistics, this definition I took from Pagano and Gavreau, it's a great intro stats book, is just the study of the collection, organization, analysis, and interpretation of numerical data related to biological and health sciences. So there's a lot of pieces in there. And biostatistics and machine learning are not separate. You know, machine learning, I think, is a tool that biostatisticians also use. And sort of many of the topics that Dave just discussed are also things that statisticians use. But the tools and the approaches that we choose really depend on the goals of the analyses. For instance, if we're doing just a descriptive analysis of a data set, then a lot of the methods we'll be using are a lot of the things that Dave just talked about. We want to just get the data together, we want to wrangle it, we want to find efficient and meaningful ways to slice and sort the data into representative summaries that we're interested in. And that can be really important. We can get hopefully better figures and representations of the data that I have right here. This is, you know, what's a statistics talk without at least one terrible figure? So I chose this because it's my favorite terrible figure. But the goals of our analyses are important. And so that's really what I'm going to focus on today is the goals of an analysis for, say, what I would consider a more traditional statistical analysis versus the machine learning approach. And that really gets down to the difference between association and prediction. And so to set this up, let's just say, suppose we're interested in the relationship between some environmental exposure, say air pollution, or specifically exposure to ambient levels of particulate matter that's less than 2.5 microns. And we want to know if that has an effect on anxiety symptoms in some population that we're interested in. So our data might look like daily measurements of PM 2.5 collected from air quality monitoring sites. And then we'll combine this data with health outcome data that we have from a large sample. And this is, again, where all of these big data techniques need to sort of work together in harmony, data harmonization, as we have multiple streams of data coming in. We have one from continuously monitored air pollution monitors, that those data need to be sort of cleaned, checked for missingness, put into a format that's usable. And then we also have data coming from sort of a large cohort study or a sample from a population. That data also needs to be cleaned. We need to understand what all the variables mean. We need to have a data dictionary. We need to be able to interpret everything. So all this stuff has to come together. And some of the goals of a typical analysis like this, where we're looking at the relationship between an exposure and an outcome, right? So if we're doing an association study, we might come up with something like this. This is taken from a paper. This is just the title. I mean, it has the word association in it. And this is a work that I did with Vivian Pung and Helen Su, who's a co-investigator on CRACE. An association study, we use general linear mixed models. And the conclusion of an association study looks something like this, where it's a very specific wording, adjusting for socioeconomic status, age, sex, race, ethnicity, year, season, day of week, region, urbanicity. So, okay, let's keep all these in constant. A 5-unit increase in PM 2.5 exposure was associated with a 61% increase in the odds of testing positive for an anxiety disorder. All right? So we're able to quantify and explain the effect of PM on an outcome. And we'll say, if you change PM by this much, your odds of the outcome change by that much. You change, PM increases by 5 units, the odds of the outcome increase by 61%. That's an association study. And that's a very specific type of analysis where we can determine and explain the effect of each individual component that goes into that model. Another type of study we might be interested in is a prediction study. And in a prediction study, our goal is sort of to say, based on all the observed data, which, say, unenrolled individual might be most likely to develop an anxiety disorder. Okay, so it's a very different type of study. This one, we're interested in saying who in this study is most at risk, perhaps, but we're not really interested in saying why that person might be most at risk. If the true goal is prediction, we just want the best possible prediction. We don't necessarily want to waste any information on trying to determine what contributes to that prediction. So this is a nice figure taken from a great book, An Introduction to Statistical Learning. If anybody's interested in a real good primer of machine learning, I would highly recommend this book. But this sort of captures the idea of association versus prediction and the different models that we use. If we look on the x-axis, we have this word flexibility, and then we have low and high. Flexibility, that's flexibility of the model. I think we can think of this as complexity, how complex your model can get. That's sort of how flexible. And then on the y-axis, we have interpretability, and that's interpretability of the model. What can we tell from it? High interpretability would be something like kind of the description I just gave, that a 5-unit increase in PM results in a 61% increase in the odds, controlling for these 6 other factors. And low interpretability would be sort of more like a black box method where it's, we don't know why, but people who have this particular set of measurements are more at risk for a disease. And so we can see the methods that have sort of that are the least complex tend to have the highest interpretability. And those are things, generally, the regression type methods. And then as we get a little more general, a little more complex in our methods, we lose a little bit of the interpretability. And I'm going to focus today on talking a little bit about one of the most common methods in statistics, the least squares, or just general sort of regression methods. And I'm going to talk a little bit about how to interpret them, why they're sort of high in interpretability, low in complexity, but they're also, as they can be made more flexible, more complex, that we then sort of start losing some of the interpretability, and then we start needing some more methods that Jennifer will get into. And so this is the basic idea of how we conduct our studies. Is from a population, we take a sample, and then from that sample, we try to make an inference about the population. And we base our conclusions on a single sample, but we need to recognize that if I took a sample, and Dave took a sample, and Jennifer took a sample, we have 3 different samples made of potentially 3 sets of distinct people, and those samples will look different. We'll all get different numbers. So we need to recognize that extra variability or uncertainty when we take those samples. And so we have to, we can't just say, we take a sample and say, okay, the average is this number, and bounce on it. And I'd say we can also think about this in terms of machine learning, is sort of done the exact same way, except replace that word inference with prediction, or some such statement. We take a sample, we use that sample, and then we get that to make predictions about the population. So from this point on, all the data you're going to see is completely fabricated, so don't take any of these results as saying, that this is what causes or influences birth weight in any way. So this is my example here. I've generated 200 birth weights from births from a population of interest, and here's a histogram of the birth weights. All right? And the first, might not be the first thing that you notice, but if you look at this, and has anybody ever thought, why do Why are babies not all born with the exact same birth weight? Right? Well, we know why. Well, we know some of the reasons why. Right? And that's what we're trying to get at with our linear models and our predictions and our associations. Right? Because if all babies are born with the exact same birth weight, then I guess, life would be pretty easy and we wouldn't have to worry about anything. We wouldn't have any, we don't want to modify any exposures. But that's not the case. Babies are born with different birth weights. So why is that? What can we look at? What are the exposures we can look at? What are genetic factors we can look at that can help explain why two babies born on the same day in the same town, mothers the same age, have two different birth weights? Why? Right? There's a lot of factors, and that's what we're doing. So we're collecting all this data to figure out which of those factors are contributing. Why is somebody at one end of the spectrum versus somebody else at the other end? So let's just say we're interested in studying the effects of air pollution on birth weight within a specific population. And for our 200 full-term births here, we collect data on the mother's age in years. The mother's smoking status, we'll do 1 for smokers, 0 for non-smokers. And PM 2.5 concentration collected from the closest monitoring site. And we have a couple of questions we could consider. Does there appear to be a relationship between PM 2.5 and birth weight? Okay, that's a pretty big question. We can answer that probably pretty quickly. Can we quantify the association between these predictors and the outcome of interest? Okay, so now we're looking at how much a change in one affects a change in the other. And can we predict birth weight based on these maternal characteristics? A very different question. Okay, so this could be the first question. Does there appear to be a relationship between PM 2.5 and birth weight? Well, so here's my measures of PM 2.5 on the x-axis and birth weight on the y-axis. And if you look, there's quite a bit of variability, but there definitely appears to be sort of this downward trend as PM 2.5 concentration increases, birth weight seems to decrease. Okay. We can fit a line to that. Just a standard least squares regression line. And we get that our sort of average birth weight, we can make a prediction, or we can predict the average birth weight is 4,172 minus 67 times PM 2.5 measure, okay? So what does that mean? Well, when PM 2.5 is 0, the expected birth weight would be 4,172 grams. And then this slope term is the sort of how we quantify the association. Okay, well, as PM 2.5 increases 1 unit, birth weights decrease on average by 67 grams. So we can make a statement here and say, for every 1 unit increase in PM 2.5 exposure, our expected births tend to be 67 grams lower. A very simple, basic model, highly interpretable, not very complex. We have one term. All right, well, let's make it a little more complex. All right, it's tough to see here, but we have these little blue triangles. Those are the births that correspond to the mothers who smoke. Okay, so maybe smoking has something to do with this, and if you look, it's kind of like, if you look at that 4,000 birth weight cutoff, there's only one mother who smokes above that, the rest are below, so, maybe that has something to do with it. Smoking might influence birth weight. So let's add that to our model. We'll control for smoking. Okay, so we get a slightly more complex model. We actually technically kind of get like 2 lines. We get, again, another equation for our line. But here, again, our intercept is now when PM 2.5 is 0 and when smoking status is 0. So this is for non-smokers. So if we have a non-smoking mother with 0 PM 2.5 exposure, the expected birth weight would be 4,194. And then the effect of PM is sort of similar, and we can still interpret it the same way. Say, okay, for every increase in PM, if we keep smoking status constant, we don't change that at all, then the birth weight, well, corresponding birth weight decreases by 64 units. So with adding smoking status like this. Again, this is still a very basic, not complex model. It just sort of shifts everybody up or down, depending on that variable. If their smoking status is 1, they kind of shift down a little bit by 311 units. If their smoking status is 0, they don't shift. We just get these nice 2 lines, they're parallel. So there's no influence of PM on smoking or smoking on PM. It's just like smoking status just shifts everybody independent of PM exposure. Very basic model. Okay, let's add a third variable, mother's age. I was really toying with how to represent all these things on one plot. So we've got this nice little color gradient for mother's age. Red are older mothers, green are younger mothers, triangles are still smoking status, PM 2.5 still on the x-axis. Okay, and we can kind of look and think, what's going on? It's a little harder to tell now. We're getting, our data's a little harder just to look at and tell an answer. This is why we need statistical models. We can't just look at this like we looked at the PM 2.5 and birth weight figure and say, oh, it looks like there's a downward trend. And even with the triangles and the circles, we could sort of start picking apart maybe the triangles are a little lower. But now we have this color gradient. It's really hard to just look at this and say what you think all of these relationships might be. So we need statistical tools. We need modeling. Same thing. Here we go. Just did a bigger model. All interpreted the same way. We find an effect of PM. We can get the effect of smoking status. We can get the effect of mother's age. Here, I'll just go with mother's age. For every year increase in mother's age, birth weight increases by 37 grams, say. Keeping PM 2.5 concentration and smoking status the same, constant. And now I can't just put 2 lines on this because I have 3 variables. I no longer can just put 2 lines. I have to sort of look in phases. Okay, so if we just look at the mothers who are 18 years old, we get this association between PM 2.5 and smoking status. Again, blue lines are smokers, black lines are non-smokers. If we look at mothers who are 25, we get this association. If we look at mothers who are 35, we get this association, okay? So still, even though we have 3 variables in here, it's a fairly interpretable model. And you can judge how well you think this fits the data, how well it explains the relationship. We can also talk about effect modification. What if we want to say, well, maybe since PM 2.5 is in air pollution exposure, and it's a very, very small particle. The reason we're concerned about PM 2.5 is they're very, very small, so they go the deepest into the lungs. They can go all the way into the very smallest parts of your lungs. So maybe mothers who smoke might have a different effect of PM 2.5 than mothers who don't smoke. Okay, well, our previous model said the effect of PM 2.5 was the same no matter if the mother smoked or not. Smoking changed the outcome, but regardless of smoking, an increase in PM decreased birth weight by the same amount. Well, now we want to say, well, what happens if we think smoking status changes the effect of PM on birth weight? And that's effect modification. Say smoking modifies the effect of PM. So we end up with a model. Oh, I did have an equation here. Didn't think I did. We end up with a model where we put an interaction term, or we multiply PM 2.5 by smoking. And what that does is, for those mothers who don't smoke, we have what looks like a very simple model of just an intercept, the effect of PM, and the effect of age. And then mothers who do smoke, they have both a different intercept, so that's going to be like having those 2 parallel lines, where one is just shifted down. But now PM also has a different slope than the mothers who don't smoke. So now they're not going to be parallel anymore. And we're going to get 2 lines that look like this. You can say, well, if PM concentration is very small, close to 0, there's kind of similar predicted average birth weights. But as PM increases, for mothers who smoke, the effective PM sort of is larger. It's bringing birth weights down faster than the effect of PM for mothers who don't smoke. And I don't think I put the actual numbers in here, but you would just see sort of that's what's going on here. Okay, so now we're getting into a slightly more complex model, slightly harder to interpret, but still, we can explain this, and we can, just say, okay, PM seems to be having a larger effect in mothers who smoke than mothers who don't on birth weight. Okay, what about a three-way interaction term? What if it's mothers who smoke who are older or younger and PM? What if PM and smoking and age all work together, right? We can write out the model just as we did before. We have a few more terms. We can write out what the line looks like for mothers who smoke or who don't smoke, and we can write out the line for mothers who do smoke. Now we have different slopes and associations of PM 2.5, depending on both smoking status and the mother's age. And again, we can't really look at this at once. This is a very complex. I struggled with how to represent this, so I went with solid lines for non-smokers, dashed lines for smokers, and the colors roughly correspond to the color gradient for mother's age. So the older mothers are in red. The middle, so I think it was 25-year-old mothers are in yellow or orange. And then the youngest mothers here, the 18s, were in green. And it's still sort of informative what's going on here. It looks like in the youngest mothers, PM and smoking don't really affect each other because those lines are parallel. So across all levels of, both levels of smoking, the effect of PM doesn't seem to change. In the orange and the middle mothers, it's sort of maybe changing a little bit. And in the older mothers, we see sort of the biggest change in those slopes. We're getting really complex here with these three-way interactions, and we're getting tough to represent, tougher to interpret, and also these things end up also being a little more sensitive to sample size calculations and things like that. And that's why we can keep going in these directions of linear regression. We can keep going and making things more and more complex or complicated if we wanted. So we can look at other associations like this. This is a local regression. This sort of, instead of using all the points to get one regression line, it moves along and sort of, you can think of it going from left to right, collecting a set of our data, fitting a line, and it just keeps sliding over and fitting a new line and a new line and a new line, and combining all those, and you get sort of this a slightly different looking representation of what the association between PM 2.5 and birth weight is. And what this would say is, okay, so PM 2.5 seems to have a negative effect on birth weight till about 10 units, and then the effect sort of gets a little steeper, and then it levels out. And that's, again, we're getting more complex. We're losing a little bit of interpretability. I can't say for every 1 unit increase in PM, birth weight is decreasing by 67 grams. I have to sort of look at this in chunks, and I have to sort of describe it that way. Another issue, as we move towards more complexity, is the idea between this bias-variance trade-off is a big topic. Bias is sort of how far off you are from the truth, and variance is how much this relationship that we've estimated would change in a different data set. And the higher the variance, the bigger the change in a different data set. And in general, the more complex your model is, you hope to get closer to the truth by adding this complexity, by adding more terms, by adding a three-way interaction, by doing all these things. The reason we do this is trying to better capture the true relationship, to do the local regression. But that trade-off of getting less bias by getting closer to the truth usually results in more variance. And for an example, I just generated a new set of data, and the regression line, the original regression line of just birth weight equals PM, very simple. That is in red. That's from the old data, and for this new data set, the same line that I generate is plotted in blue. They're very similar. Right? So the relationship looks the same. But if I do that local regression on the new data, The old data, that's the line we saw before, and here we have the new data. Okay, so both of these lines, you might not know, depending on which one you got, which one would be true, but they have very different interpretations. In the first one, you'd say, oh, look, like, the effect of PM, it's like in the very beginning, it seems to be birth weights are increasing, and then it decreases, then it drops off steeply. And the old data, you'd say, okay, at the beginning, as PM increases, birth weights are decreasing, and then it levels out, okay? So this is an example where the same model fit to two different data sets can give you different results. This is an example of high variability. Less easy to interpret. And depending on the goals of your analysis, you want to choose which of these types of modeling procedures you want to pursue. And as we talk more about sort of the high variability and different types of fits to model, we move closer from linear regression to some of these machine learning methods that Jennifer is about to talk about right now. So that's it. Okay, thank you.
Thanks, Justin, for giving a good segue for my piece, and thanks, Dave, too, for giving an introduction for the whole talk. So, hello, I'm Jennifer D. My research is in machine learning. So, what I planned today would be a really brief tutorial on machine learning, and I want to let people know that this is in by no way exhaustive. But I'll just give you a little brief understanding of the various techniques that are commonly used. So first of all, what is machine learning? So machine learning is a field that deals with algorithms that allow computer to learn from experience in performing some tasks. So basically, in this field, we're focused on developing algorithms that make computers more intelligent by learning from experience. Now what is experience typically? Typically, experience can be in various forms, and in our context, it would be through data. So that's why it's closely related with statistics, because experience will be in the form of data that we've collected, that we've learned from the past. Now, I like this cartoon picture to showcase. They can't see me, right? So I should use the mouse. So this is I like this block box picture to explain a typical learning algorithm. So you have given input X, and X would be in the form of features that you've collected in this big data problem. In our case, the PROTECT data would be all the clinical variables and product usage of patients that we've collected would go into X. And then our goal is to predict Y. And Y in our case would be preterm and term outcomes, or other variables that you're really interested to see the relationship between input X and Y. Now, a learning algorithm, think of that as some function approximator or a model to learn, given input X, what would be your output Y. Now, the two popular settings in learning is supervised and unsupervised. I'll give you a short explanation of how they differ. So how do we learn a model, a learning algorithm, from our data? So what do we typically do? We collect data samples, right? We collect a lot of data, X, and I'll call this Xi for each sample that you collect. So you have Xi is a vector of features with D dimensions, how many features you've collected. And for each patient that you've collected, usually you'll have a label Yi that describes whether you have preterm or term. So Y would represent the output of interest. So you'll collect several samples, let's say N samples of this, of data, and you usually get a table that looks like this. You have each row is the patient, and then you have several features that describe that patient. All these values would be your X vector. And then you'll have an output variable that you're interested in. And this could be term, preterm. This is a different data set that I have. But you can have whatever Y is would be the output of interest that you're trying to predict or learn. So in supervised learning, your goal is to learn a model, learning algorithm that tries to predict Y given any new instance X. So again, I'll try to repeat this. So basically, the goal is to learn a model, a learning algorithm for predicting Y given X. To do that, you first collect data. We call this our training set. And in the training set, so each sample, patient 1 to N, that represents your past experience. The data you've collected represents your past experience. Now, this is called supervised because here you have a teacher in the form of labels. So in a supervised learning setting, for each patient, we know the label Y, the value of Y for each sample. And you use this relationship to learn a model. But eventually, after you learn a model, I'll call a learning algorithm, we'll show you later that it will be some form of f of x, a function approximator. For any input x, you'll use that for new data x to predict Y. Now, how is this related to regression that Justin said? If Y is continuous variable, you have a regression problem. If Y is a categorical variable like us, term and preterm, it becomes a classification problem. Now, in unsupervised learning, the only difference between supervised and unsupervised is that during training, you don't see Y. You don't have any, you're only getting samples, but you don't know what the outcome of that sample is. So that's the only difference. So two different settings depending on what your data looks like. You have those two different scenarios, but the goal is still the same, usually. Your goal is to predict Y given X, but you didn't see that in your training set. Now, I'm going to give you a tutorial on several supervised learning algorithms that are widely used and available in toolboxes so that you have an idea of what's underneath the hood of those methods. So the most popular approach is linear regression. So as I said, a learning algorithm, you can think of that as a function approximator. Let's call that f of x. So this is a function approximator of that we want to learn. Now, to do that, you have to have a model of f of x. The simplest model is a linear model. So a linear equation is W transpose x plus b, where W, you can, for those who are not engineers, W are coefficients you assign for each feature. And then W transpose x just means that you have a sum of, how do I do this? Okay. Basically, this is what Justin showed you. You have that FM times the coefficient plus smoking times the coefficient. So W will represent those coefficients that you need to learn, and X represent those features, FM and smoking. And B here is just an offset of your line. So in linear regression, your model, you assume that f of x is a linear function. And the goal here is, given a training set of samples, I from 1 to n, that table that I showed you, the rows of patients, I want to learn what W should be, those coefficients, and what this offset should be. And typically what you do is you minimize a loss function. And the most simplest loss function is the squared loss. So basically you have output for each ground truth Y in your training set minus your approximation, which is f of xi, and you want to minimize this. So Y minus f of xi, I cannot point with the mouse. It's okay, so yi minus f of xi squared, you want to minimize that. This is a squared loss, okay? So you want to minimize that. Now, So basically, you have a training set of samples. You want to find a line that fits the training set well. The problem is, you can fit that well, but the problem is that note that our goal is to predict data you have not seen, right? New samples. And as Justin showed you a picture, usually a training set is just a small view of the whole population, the real underlying distribution. You only get samples from a real underlying distribution. So I'm trying to fit this line, and the problem is that you might overfit your training set, meaning you may be able to fit the training set well, but not data that you have not seen. So to avoid overfitting, also called as generalization in machine learning, one way people avoid overfitting is to add a regularizer. One way to avoid overfitting is to make sure that this weight, the coefficients don't go so high. Don't get too large values of W. So to do that, you want the norm of W to be small. And a typical norm people use is the L2 norm. L2 norm is just each coefficient squared, add them all up, and then add them all up, that's your W. So the squared sum of all your coefficients is that W norm squared. So you want to minimize this. You want to minimize this first term so that your model fits your data and make sure that it doesn't overfit it. So you add this norm 2 squared regularizer. Now adding the regularizer is called ridge regression. The ridge regression models, when you see it in toolboxes, is actually modeling this loss. Now, another way to regularize is to use an L1 loss. Now, the nice thing about an L1 loss is that it pushes a lot of the coefficients to 0. By doing that, you're also doing feature selection. So when you do, it will do regression and feature selection at the same time. And when you look at toolboxes, that's the lasso algorithm. Okay. Now, again, a lot of learning algorithms have this form. You have a fit term so that it fits the training set, your data, and a regularizer so you don't overfit. So you'll see that a lot of models has this mechanism. They're not on the same slide?
I think that might be.
Okay.
Sorry.
Yeah, because I have animations, so I don't know if that complicates things.
We lose the meeting, maybe?
Maybe we lost the meeting.
Oh, boy.
You're doing a good practice.
Okay. Okay. Was that too mathy? It's okay. Okay.
That was just the right one.
Okay. I understood.
You're in the meeting. We can hear you and we can see you. It looks like it's just a screen that you don't have.
Yeah, Laura, if you just try to go ahead and share it again and try to get to that slide that she was on, that would be good.
Yeah. Problem is.
So stop sharing and then share again.
Yeah, you should still be the presenter. You should be able to, is it not letting you pull it up?
Can you see the slide now?
Says learning problem?
Do you see learning problem?
I am not seeing the slides. Is anyone else?
Yeah, I'm seeing the slides over here.
Okay, good.
And now it's in the presenter mode. Oh, there it is. Viewing mode.
Did you share an application
They're sharing a screen.
as a screen?
So do you see a slide that says learning problem?
Yes, he does.
Do you see learning problems?
Yes, we see it.
Yeah, I do now too, Laura. This is Kristen.
Categorical for binary classification is 0 or 1, but the output of a regression is a continuous valued number. How do you turn this to 0 or 1? So what we do is, we use this linear regression function and put it inside what you call as a sigmoid. A logistic regression function is shown here, 1 over 1 plus e to the minus w transpose x plus b. And what the sigmoid does is like this. So the x-axis is the output of the simple regression line, and then the y-axis turns it to a value between 0 and 1. Okay? And basically that's all what a sigmoid does. And it's in a continuous form so that it's differentiable and we can do optimization on this model. So this is that's basically logistic regression. So in logistic regression, what changes is that instead of a linear model, now your f of x is a logistic function. And again, you're doing the same thing. You're minimizing the squared loss plus some regularizer. So if you're doing, so that's what logistic regression is. Okay. That's it. Are there questions so far?
I think we'll take them at the end.
We'll take it at the end, okay. Now, another very popular method is support vector machines. Is a really nice classification algorithm because it provides an objective function that's convex, meaning that learning the model will give you given a loss function that's convex, you can get the optimal solution. Now, what does a support vector machine, how does it work? So a simple geometrical view of the problem can be presented this way. So this is a scatter plot in 2D, a very simplified example. You have negative examples in gray and positive examples in red. Okay, so let's say this is the gray ones are the term, the red ones are the preterm, for example. Now, if I have my training set, my data samples that looks like this, and I want to design a classifier that separates these two classes. Okay, let's simplify the problem. I want to find a linear classifier that separates them. I want to find a line that separates them. Which one will you pick? Red, orange, or blue? Note that they all would give me 0 error on this data, right? Which one will you pick? You'll probably pick orange somehow, because if you pick red, it's easy to make mistakes on new samples. If I have a new data point that's close to that red line, I probably make mistakes on assigning it as a negative class, even though it's positive. And similarly for the blue, I'm easily going to make a mistake also of assigning them as the red class, even though it should be gray. Okay, so in support vector machine, what it does is that among all those possible solutions, it'll find a line that tries to do the following. So the general intuition is to find a classifier such that if I draw two parallel lines from this orange line until that line, hyperplane, hits the first red dot, and another line that hits the gray dot, okay? You want the distance between these two parallel lines to be as large as possible. This distance between parallel lines is called the margin. Okay? Now, again, what does a linear classifier look like? A hyperplane? A hyperplane is defined by W transpose X plus B equal to 0. That's a hyperplane. And without loss of generality, we assume that this positive hyperplane that hits the red sample is W transpose X plus B equal to 1, and this other plane hitting the negative example as equal to -1. Note that I'm not losing any generality because I can change B to any value. So 1 is really arbitrary here, and I can also learn W to be any value. So note that. Okay, so we simplify the problem this way. Okay. Now, so basically, what we're trying to do is to find a hyperplane that maximizes this margin. Okay. Now, this margin geometrically, given those equations, is equal to 2 over the magnitude of W, which is just the norm 2 squared of W. So I want to maximize this. I can translate that to minimizing the norm 2 of W. So basically, maximizing the margin is equal to minimizing this norm 2 squared of W. And in addition to that, another thing I want to do is that, what did I say? This hyperplane that hits the red dot, right? It's the first red dot it hits. So it means that what I want is that all the red dots, the positive examples, should be larger than this plane. Okay? So that's defined by a constraint that W transpose Xi plus B should be greater than or equal to 1. And that's true when this red dot is positive, so when Yi is 1. So if I multiply that by a positive value, I can write this way. In addition, the negative sample should be below this gray line. Okay? So therefore, again, if Yi is minus 1 to represent negative example, I can simply write it as an inequality constraint shown here. So in support vector machine, the goal is really, it's an optimization problem where I want to minimize this norm 2 squared of W subject to this linear constraint. And that's it. Okay, so that's what it does to learn the W and B. And the nice thing about that is convex, because this is quadratic with linear constraints. Okay, now after you learn the W and B, how do you classify new samples given new patients X? So what I do is, really, I see if, after I've learned W and B, given new X, I look at the sign. If it's positive, it belongs to positive class. It's the sign of W transpose X plus B. And if it's negative, it's a negative class. Basically, what I just said is this sign of W transpose X plus B defines this orange boundary here, hyperplane. So those above the orange hyperplane belong to positive class. Any points below, lower than the orange boundary is classified in the negative class. Okay. Now in support vector machine, why is it called support vector machine? Because this circle point hitting the parallel planes, these are called support vectors. And the nice thing with support vector machines is that the decision boundary, the orange line, is actually just defined by those support vectors. Okay, so given lots of data, in the end, what this learns is that what affects the W when you solve this optimization problem, what affects this W are just these points on the boundary, on the hyperplane. The support vectors are the only one really influencing, determining this orange line. Now, what's nice about that is that it's robust to outliers. So if in my training set, if I have points really far from the boundary, it doesn't affect my classification. But if I do regression or logistic regression, it will be affected by those points far from the boundary. So that's a nice with support vector machines. It's robust to outliers. Now this is nice, but my sample shows perfect training set where I can find a line with no errors. What if I have training set with errors? I have blue, I have gray points on the side close to the red, and red points close to the gray. What do I do with this? And typical data looks like this. How do I deal with that? So a support vector machine, what it does is that it allows slack. So it allows for room for error. So they call these, so what's going on? This gray line should be on this side. So that distance is represented by slack variable psi j. Use the mouse. Okay. Okay. So basically this gray line or blue line, depending on your projector, this dot is on the wrong side. So how do I represent that error? I represent it by the distance of this blue from where it should be. I call that psi j. And then I also represent the error of this red point to be the distance of this red point to where it should be, which is here, and that's represented by psi I here. So now I change my objective function as that margin loss, which is that W squared, norm 2 squared, plus this, I want also my errors to be small. So I want to minimize both the sum of the slack variables for all my points, my errors, plus this norm 2 squared. And again, subject to the constraint that the red point should be above the red line and the blue point should be below the blue line, plus some slacks. That's why I'm adding this. So this is the most common version of support vector machines that's actually being used. This is the soft margin version, which allows for error. Okay? Now, what do you see here? Okay. What do you see here? You have a fit term. Okay. The slack variable, the errors, is the same as the squared loss error that we have with regression. You have a fit term and a regularizer. It's very similar. It has that. The only difference is that you have this constraints that red point should be on the red, above the red line, and blue point should be below the blue point. So, but it's very similar. So they have similar flavor. Okay, and another way to write this objective function is the hinge loss summarized here in the bottom because it looks like a hinge. Now this is all well and good, but it's still a linear classifier. Right? How can it deal with more complex shapes? So the idea is, if it's to deal with complex shapes, we apply a nonlinear function. So instead of a linear W transpose X plus B, now X, we map it to some high dimensional space. So for example, I have data like this. What if I have a positive class here that looks like this, and negative class surrounding that? Now I can't separate this by a line, right? So what do I do? So in nonlinear SVM, you map them to some high dimensional space. So you map X to phi of X, such that in this high dimensional space, I can find a boundary, a plane, a line that separates the two classes. So that's the trick in SVM. But it doesn't do this mapping directly with phi of X. It does so through kernels. So what's a kernel? Kernel is just a function of the input variables, xi, xj, such that it's equal to the dot product of those samples in high dimensional space. So the nice thing about the kernel trick is that really instead of first mapping X to phi of X and then taking a dot product in that high dimensional space, which has more calculation, more operations that you need, we do everything in kernel space where we just use kernel function of the input variables xi, xj, which are in a lower dimensional space. The computations are safe. And in SVM, you can do this because all the operations you need between xi and xj is in the form of kernel. So you can work everything out through kernel. And again, the nice thing is that even though you map them in high dimensional space, it's nonlinear. The objective function is still convex, and you can get a global optima. So that's why it works really well, because you work with local it's convex and it's global. Okay. Now, SVM used to be the best method out there that works really well. Nowadays, another algorithm called neural networks are becoming popular again, and it shows a lot of good performance in a lot of different fields, especially in computer vision with images and with speech. Okay, so let me show you what a neural network is. So in a neural network are composed of units called neurons, and a neuron, the circle here, is comprised of really something very basic. It's a linear regression of your inputs. So you have a sum of wi, xi plus b. So it takes in all those inputs, multiplies by w, and adds an offset. So you first do that. So a neuron, that's a linear combination of your inputs, followed by an activation function F. So basically, each neuron has this operation, F of a linear combination of your inputs. Okay? And note that the weights are assigned on the links of going into this neuron, the circle here. Now, what is F? Again, what we like our activation function F to be is like a threshold function, so that it maps your continuous space to a categorical value between 0 and 1. So this is an example of an activation function, step function, but we don't want to use step function because we can't take derivatives for that. So we usually use, again, a sigmoid shown on the right. So similar to logistic regression, we use the sigmoid. So this is the common neuron used in neural net. The basic unit usually is linear combination of input followed by a sigmoid, which is like logistic regression. Now, the more modern neural nets use this ReLU activation function, which looks like this, shown on the slide. Now, given this, okay, a neural net is really combining a lot of nodes so that you can have a more complex representation. So the idea is now I can have an f of x that's more complex by connecting each node to other nodes that looks like logistic regression nodes. Okay, so that's what neural nets is. So each node looks like logistic regression nodes. Now, another thing is that I've shown you that usually we add regularizers. So in modern neural nets too, they have regularizers. They add logistic regression with L2 or L1. So you note that in toolboxes you have those options as well, again, to avoid overfitting. And here it shows the softmax, meaning if my output is not binary, if I want it to be multiple classes, you can use a softmax function. It's called softmax because it's a soft version of a max function. Now, the most common neural net uses convolutional layers. So what's the difference? So in a deep network, all the inputs are connected to your nodes. Okay, so that's called the dense unit, that dense layer. Now, for images, note that in images, typically the features would be the pixels in an image. And in images, only the neighbors are important in predicting how it affects your center pixel. And typically in images, what you want is you want to learn filters. So in image computer vision, what you usually do is you first extract features. Given raw pixels, you extract features using Fourier transform and so on. And what are Fourier transforms? There are filters. And the nice thing with convolutional neural net is that you try to learn, so what are filters? Filters are just a box that you go through your image, a sliding window through the image, and change them by multiplying. Yeah, if you don't know, it's hard to explain. Anyway, so you need filters. Basically, you just look at the spatial neighbors to influence the center pixel. That's what filters usually does. And instead of predefining the filter, in a neural net, you learn the weights. You learn what filters to use. And that's why it works really well with images, because instead of predefining what filters to use, you learn those. And by stacking layers, you actually have very complex operations. So what neural networks can do is can learn end-to-end. You don't need to extract features. You start from raw images and then go to classification and predict that object, cat or dog, and so on, which they usually do in object recognition tasks. Okay, maybe I'll continue, or
So maybe 1 or 2 more minutes.
1 or 2 more minutes. Okay. I have more comments about this, but maybe I'll skip. Okay. Now, another classifier is the decision tree classifier. So neural nets are powerful because it can learn very complex functions. An f of x that is highly nonlinear and complex, but you don't know it's hard to understand or interpret what it learns. Now, the nice thing about decision trees is that the models that it learns is more interpretable. And a decision tree looks like this. And this is actually quite useful, especially for our type of data, because for tabular data that looks like the one shown on the right, you have examples, and then you have features that describe that sample. And the goal here is to predict whether a person will play tennis or not based on features, outlook, temperature, humidity, wind. What a decision tree would do will build a tree of how to classify a given input, and it's very intuitive. So first it checks, what's the outlook? Is it sunny, overcast, or rain? If it's sunny, it goes to this branch, and then you check for humidity. Is it high or normal? If it's normal, then your classifier would say yes. Yes, that person will play tennis. If it's no, it would not play tennis. So it's very interpretable, and it's quite intuitive, similar to usually how we make decisions. So that's what decision tree would give you. Maybe I'll skip about how we learn this tree, but just show you the tree. And we have tried actually learning a decision tree on this data, on the PROTECT data. Now, the first time we run the decision tree, we run into a problem that the data is imbalanced. We have a lot of samples from normal, but few examples from preterm. So a decision tree or standard techniques usually assume they're balanced, and so a lot of the methods don't work that well. So what we did was modify the decision tree to actually, instead of just looking at class purity, in learning the tree, we look at the area under the curve, so to take into account the imbalance. And we use that to build this tree. And note that a tree like this is quite interpretable. So here, just at the root of the tree, it says, was pesticide applied, and is the frequency greater than 2? And if yes, you go to the next branch, and so on. So it helps you decide whether it's term or preterm, and you can actually understand what's going on. So that's the nice thing about a decision tree. Now, I think I'll skip clustering, okay? I have other slides to talk about unsupervised learning. When you have no labels, what do you do? Or maybe this is quick. One of the common methods for analyzing data is clustering. Clustering is the process of grouping samples. So this is a very common approach for unsupervised learning. It groups samples by grouping together samples that are similar into one cluster and samples that are different into other different clusters. But the problem is, how do you define similarity, right? So different algorithms vary based on how they define similarity. And it tells you the type of clusters it can find. So k-means uses a similarity based on Euclidean distance, meaning it will find clusters that are spherical. So if I have data that looks like this, and I try to group together samples that belong together, k-means would find these 4 clusters, and it's nice. It works well for this data because they're spherical. But why is my data looks like this? K-means would, again, when k equals 2, it will find clusters like this that are spherical. So maybe a more appropriate clustering algorithm for that would be a Gaussian mixture model, which instead of spherical groups, it will find elliptical groups, like ellipsoidal groups. So a Gaussian mixture model will find Gaussian components and can find this cluster as well. But what if your data is more complicated like this? Green, blue, and red are different clusters. You can't use k-means or Gaussian mixture model for that. So a technique that's nice for that is spectral clustering, which defines similarity in a nonlinear way. So that's why you can find those clusters in both these figures. And that's it. Just last is that, why did I spend a lot of time explaining what's under the hood about these models? Because when you apply machine learning, although it's easy now because there's a lot of tools, I want to give a warning that it's good to know the assumptions and limitations of this algorithm so that you know what you can get out of this method and make proper conclusions. and also a lot of off-the-shelf, like we showed earlier with the decision tree. Because of the imbalance data, sometimes they don't work as is. So it's good to actually understand them so you can design properly what's the appropriate one for your data. So I'll end here.
Thank you, Professor D, Professor Cayley, and Professor Mangiarides. I don't have any questions online on the chat, but if someone has a question online and would like to take themselves off mute, you are all on mute at this point. Please do.
Hi, this is Jose, and thank you all three of you. This is just fantastic. I have general questions, and maybe start with Justin. And it's when you're looking at the more complex models that I think it was in the LOESS, it showed how two graphs actually differ quite a bit, and then the question is how do you pick one versus the other? And the question is, what about how do you take into account perhaps other data that I'm thinking more if we're looking at preterm and certain particular variables, the use of data may come from, say, experimental animals, and how can that help perhaps give a direction on which lines to follow or how to interpret the data when you have divergence in terms of the possibilities?
Yeah, so that's a tough question but so that's a tough question. How do you choose which line? I think that gets at this underlying question of sampling variability, because really the example that I showed was just an example of sampling variability where if we had applied this model to a second sample, what would it look like? And usually we're in the situation where we just take a single sample. And so I think really the key to that is sort of in the explanation and dissemination of the results and of the models, of making sure to sort of recognize that that there are other factors that are influencing these relationships that we might not know or might not be able to quantify. And I think there's a lot of caveats in a lot of these methods already about sort of performance in the tails, and as Jennifer touched on a little bit, and I touched on less, sort of the effect of outliers and highly influential points and leverage points and things like that, and sort of more of the data pre-processing. But yeah, I mean, I think that's a big, if I'm sort of getting at what your question was, I mean, I think that's, a bigger issue around how, the replicability. Yeah, you could also, you could do cross-validation on the data also to show like how much your model will change with slight changes in your sample and things like that. So yeah, I think that's a good sort of way. In statistics we have our model fit metrics, and I think in machine learning it's cross-validation focused, but I think they can be used in both.
Yeah. So actually, if you've noticed, there's a lot of overlap between statistics and machine learning, and I think the nice way is really to combine both to really figure out what's going on. So so for this data, we have a lot of features. So really, to deal with this, if you really want to find that needle in the haystack, we might need to have more complex models. But then once we find it, we might need a more rigorous test, like applying some biostats on it to really figure out whether it's if that feature is really associated to what you're looking for. So we can use maybe machine learning to narrow it down, and then because if you look carefully at the biostats model, when you do all those hypothesis test type of strategy, usually you want it on a smaller set of features variables to really study and verify. So that might help. The other thing too is that often when I collaborate with with clinical folks, they forget that, data analysts forget that actually we have access to a lot of experts. They do have some good guesses about what's going on, and we can also leverage domain knowledge to help us, like focus.
I think it's just sort of feature engineering as
Yeah.
opposed to just feature selection, where you're pre-specifying potential forms of the features, the covariates. You're pre-specifying potential combinations, interactions that might be useful as well.
Another thing too, since we have everyone here, that as you notice, a lot of the models that we use or tools that we use rely on the training set. So the cleaner we get those data, the better it helps us. And then another thing too, as we start to wrangle this data, one of the things we encounter that's really difficult is missingness. Missingness, like extreme missingness, that we have one cohort has features on subset 1, and another class has features on subset 2, and then there's no overlap. When there's no overlap, it's really a hard problem. But, yeah.
Other questions?
Thank you. That was very helpful.
Well, if there are no other questions, we want to thank you all again for presenting. And for those of you who attended, if you think of questions that you do want to ask, feel free to email them to me. This is Kristen. You would have gotten the invite from me. And we will post the recording very soon and let you know when it is out there. Thank you again to our presenters.
Hey, Kristen, it's Akram over here. Can you hear me?
Hi, Akram. Yes, I can.
Hi, I just want to thank Dave, Justin, and Jennifer. I really appreciate it. I enjoyed it, and I've learned a lot, too. Thank you for taking the time to do this.
Great. Thank you for attending.
Have a good weekend, everyone.
Bye, everyone.
Bye.